Hello everyone, I am Handan, a researcher from Web3 Foundation. Today I'm going to talk about the block production mechanism of the main chain of Polkadot, which is BAPE. I'm sure you have already heard about the name Polkadot and you probably know what it is, but let me say a few sentences about it before starting explaining the protocol BAPE. So Polkadot is a multi-chain technology which includes many independent blockchains in its structure, and it provides a network to make them able to communicate between each other in a secure way. Here you see the general picture of Polkadot. The main chain is called relay chain, and the relay chain holds the states of parachains. Parachains are the independent blockchains that I mentioned. And the relay chain is maintained by the parties called validators. And validators run the protocol BAPE. So BAPE is a proof-of-stake protocol, and it's designed similar to Ouroboros Proof, but there are some key differences. For example, it doesn't depend on any central clock. And after Genesis block is released, the timeline of a validator is divided into epochs, and each epoch is divided into small time intervals called slots. We assume that validators are in a partially synchronous network. It means that any message that they send will eventually arrive to all validators. For example, if a block is sent in a slot SL, it will arrive delta slots later. And this delta, it's a parameter and it's not known actually. I also want to explain you how we choose the best chain in BAPE. So in BAPE, there is on top of BAPE, there is a consensus algorithm called GrandPA. GrandPA just finalizes some blocks of BAPE deterministically. You don't need to know the details about GrandPA, but just know that it finalizes some blocks. And the chain selection rule in BAPE says that choose the longest chain that includes the last finalized block in GrandPA. For example, in that case, this top fork is the best chain. So before giving the details, I want to show you a high overview of BAPE. So we have a Genesis block as all blockchains, and this Genesis block includes a random number. This random number is used in the private lottery algorithm that assigns all validators randomly and privately. Here, privately means that the validators don't know who is selected. They only know if they are selected or not. So first two epochs, we use the randomness from the Genesis, and for the rest of the epochs, for example, in epoch number 3, we use the randomness from 2 epochs before in our lottery algorithm. So the rule is using the randomness 2 epochs before in each epoch when we run the lottery algorithm. So as you see, there are also some empty slots. It means that there is no validator assigned in these slots to produce any block. And in order to make the block production mechanism in constant time, we also have another block production, which is done by the validators who are assigned publicly, not privately. But these blocks only generated for the empty slots, and they are not considered in the best chain selection algorithm or randomness generation. Therefore, in my talk, I will only focus on the blocks that are generated by these privately assigned validators. So in BAPE, a validator has 2 types of keys. One is signing key to sign the blocks, and the other one is lottery key. So for lottery, we use a cryptographic primitive called verifiable random function, also called VRF. And this lottery key is used in that function. This function generates a random number with a value x and discrete key. And VRF also has another algorithm called proof that generates a proof. And this proof says that the random number generated is generated by using the secret key and the value X. And also, there is another algorithm called verify. Verify takes the public key of the random number generator and verifies the proof. So if we want to have a secure VRF, we want from that to generate a completely random number. It means that this random number should be unpredictable by other parties who don't know about anything about secret key. And we want that proof algorithm shouldn't leak any information about the secret key. And also verify algorithm should only validate the correct proofs. Okay, so now I will explain how actually lottery works. Assume that we have a validator in slot number I in epoch number j plus 2. This validator uses the randomness from 2 epochs before, so rj, together with the slot number and epoch number, and puts these inputs into the VRF and generates a random number. And if this random number is less than a threshold that we define, then validator produces a block. And as you see, since VRF is secure, this number V is unpredictable and cannot be known by any other validator. So this is secret selection algorithm. Okay, so if the random value is less than the threshold, this validator is selected as a block producer. It means that he is the slot leader, and he starts to produce block. But before that, he also generates a proof to show other validators that actually he is selected. So therefore, he puts this random value V and the proof into the blocks, and the transactions, the slot number and the epoch number, the hash of the chain that he wants to build on top of it. And after he signs all these values and generates the signature and adds this signature to the block and sends it to all other validators. Okay, so if this random value is greater than the threshold, then the validator just collects block from other validators. For example, this validator receives a block from another validator. In that case, he needs to check if this block is correctly generated. For that, we have also classic block validation mechanisms like check if the hash is controlled, hash is correct, and the signature is valid, it's sent by the valid validator, and so on. And also, validator should check if the proof is correct and this V value inside the block is less than the threshold, so that he will believe that actually this validator is the slot leader, eligible to produce the block. And if everything is okay, it just adds the block on top of the block on top of blockchain whose hash is h-best. Okay, as you see, epoch randomness is very critical in lottery. So I will show you how we generate this epoch randomness. So a validator first decides the best chain with the best chain selection algorithm, and then he retrieves all VRF values that belongs to that epoch. And for example, let's assume that these are the blocks of that epoch, and these are the VRF values inside these blocks. And then he just hashes all of them and obtains the random number. Okay, so until now I described you how validator produces a block and how actually BAPE works, but I didn't tell you how actually these validators know the slot number. So it is very critical for the completeness of the protocol, because if validators don't know about it, they will never know when to generate their block. And also it is very critical for security reasons. For example, assume that this is the real timeline, which is agreed by most of the validators. And assume that this is late validator. For example, this validator thinks that he's in slot number 3 while the real slot number was 5. And also assume that this late validator is the slot leader of slot number 3. in that case, what happens? The block production continues as I described, and when the real time arrives, slot number 3, there will be no block production because the late validator thinks that the time didn't arrive. And then the block production continues. When the late validator's timeline reaches slot number 3, he will think that he has to produce a block, and he produces the block on top of the block of slot number 2. So he can only produce on top of it because the slot numbers in the blockchains should strictly increase. And then another validator wants to build a block, and in that case, this validator will choose the longest one because of the selection rule. So the problem here is this. If we have a lot of late and honest validators like that, their blocks will not be in the longest chain, the best chain anymore. So we will not have enough honest blocks in our block production mechanism. Maybe the adversarial blocks will dominate. So we cannot guarantee anything anymore. Therefore, it's very critical to provide an algorithm to these validators to obtain what is the current slot number. And then we design an algorithm called relative time algorithm. So assume that we have a validator again, and this validator doesn't know when the slot starts or ends, and doesn't know anything about the current slot. In that case, this validator runs the relative time algorithm, and the relative time algorithm works as follows. It first collects some amount of blocks and stores the arrival times. And after that, the validator decides to learn a start of a slot number. For example, let's say he wants to learn what is the start of slot number 14. Then relative time works like that. So relative time says that if the block of slot number 1 sent on time, then SL14 should be 13t seconds later. T is 1 slot time. And similarly, if a block of slot number 3 is sent on time, then it should be 11t seconds later. So it is 14 minus 3 seconds later. And it does the same for all the arrival times. And then it obtains some candidate start time for slot number 14. And after that, he chooses the median as a start of the slot number 14, and algorithm ends like that. And we prove that if more than half of the validators are honest and they agreed on the same slot number, then this algorithm outputs a slot number which is delta behind the agreed one. So delta here is the parameter for the partial synchronous network. Here, of course, we don't provide perfect synchronicity, but we provide some bound. So we have some limit on the output of the relative time algorithm. And according to that limit, we can adapt our security parameters and still achieve that these late parties can contribute enough to the best chain. And also, we believe that this relative time algorithm can be used other blockchains who needs synchronization like us. And for example, we adapt this algorithm to Ouroboros Praos, and we obtain a new protocol called Ouroboros Clepstra, and you can find the details about this protocol in ePrint. Okay, so I want to also say a few things about security of BEP. I will not tell you the details, but I want to show you what we wanted to prove and achieve. So we proved that blocks generated, for example, in epoch J, will be finalized, probabilistically finalized at latest just before epoch J plus 2. It means that when the validators want to learn the randomness from epoch J, they will all see the same blocks and they will all generate the same randomness. And also we prove that the blocks produced in epoch EJ includes at least one honest block. Like that, we have enough randomness in our random generation algorithm. Okay, so I want to finish my presentation with few reminders or review. You can think it as like that. So BAPE is a proof of stake protocol, and we assign validators to some slots randomly and privately. So the blocks of validators are censorship resistant because adversaries cannot know who is going to produce the block. And our chain selection algorithm based on grand band longest chain rule, so we have some hybrid consensus there. And also BAPE doesn't depend on any central clock. And if you want to learn more about BAPE and if you want to see the proof, you can check our research web page. And also you can see other researchers from Web3 Foundation. And thanks for listening.